Welcome to the Circulatory System lecture. This again is going to be a little bit of review from what you learned in anatomy, but it's going to be a little bit of new information also from physiology. Now this PowerPoint will definitely lead you in to the next PowerPoint we're going to do, and we're going to start by talking about the fact that our circulatory system is a closed circulatory system. Now what that means is that we have a system where blood only flows through blood vessels. The heart pumps the blood through the blood vessels, and that blood circulates all the way around right back to the heart. We don't just have blood laying around everywhere underneath the skin. So the term closed means it's enclosed within blood vessels. Not every organism or animal has a closed circulatory system. Some of them simply have blood underneath chitinous shells or just simply in compartments. Now for humans, because our circulatory system is closed, we need to have a way of moving nutrients from the blood into the tissues and waste from tissues into the blood. And for that, we use diffusion. In the last PowerPoint, you learned about diffusion through capillary beds. There's 5 major ways of diffusion. Be sure that you go back and review those 5 ways because you definitely need to know them. Now, I combined the next 2 slides together into one so you can kind of see the entire anatomy of the heart. The cardiovascular system is a system that includes the heart, it includes the blood vessels, and it includes the blood. In terms of the heart, here is an actual heart that belongs to a sheep, and you can see the right side of the heart is here and the left side of the heart is here. We've got the atria at the top and the ventricles at the bottom. Here is a frontal view of the heart. Please make sure you remember the blood flow through the heart. If you don't, you have to go through it and memorize it. So from the superior vena cava and the inferior vena cava, we go into the right atrium, and right atrium we're going to go down to the right ventricle, up to the pulmonary arteries, and that sends blood to the lungs. So from the lungs, we're going to drop off carbon dioxide, pick up oxygen, and bring that blood back in through the pulmonary veins into the left atrium, down to the left ventricle, and up and out of the aorta. So make sure you remember that blood flow. If not, you have to go ahead and review it because you're going to need to know it to understand the electrical conduction system of the heart. Now, just to review, we have 2 circuits. In terms of how and where the heart pumps blood. The first one is the pulmonary circuit, and this is going to be the circuit that has blood leaving the heart to go to the lungs and coming back from the lungs to the heart. And then you have the systemic circuit, which pumps blood everywhere else in the body: arms, legs, head, neck, brain. So pulmonary is to the lungs, systemic is everywhere else. Now, quick review of the contents of the blood. You have blood plasma, which is the fluid that the blood actually swims in, and this houses hormones, antibodies, nutrients, gases, and wastes. Then you have the red blood cells. These red blood cells are disc-shaped cells. They are large, and they are there to carry gases like oxygen and carbon dioxide. And the way they do that is with a protein called hemoglobin. Then you've got white blood cells, also called leukocytes, and there are several different types of white blood cells. So you got B cells, T cells, monocytes, neutrophils, eosinophils, and basophils. Please make sure you know the names of all 5 types of white blood cells. Purpose of these guys is to help fight infections, and they are a huge component of your immune system. And the last piece of all this is going to be what's called thrombocytes, also known as platelets. These are tiny fragments of larger cells called megakaryocytes, and they are responsible for clotting blood and creating scaffolding in damaged tissues. They're held together by a glue called fibrin. So fibrin is the glue that holds platelets together. Now, this is the interactive part. Be sure that you understand this. Some of you might have learned this in anatomy. Some of you may not have been taught this yet, but this is blood typing. Blood typing will be tested on, so let's go ahead and do some examples of blood typing. So blood comes in 4 different types: A, B, AB, and O. The way that they're named is dependent upon which antigens are present on the red blood cell surface. All these little spiky things, these are called antigens. Notice that O blood type doesn't have any antigens. It's bare. So A blood type has A antigens, B blood type has B antigens, AB blood has both A and B antigens, and O has no antigens. They're all listed in this last row. Because A blood only likes itself, it only likes other bloods that are A blood, it's going to make an army of antibodies, and they're going to be called anti-B antibodies. Here's the rule. If a red blood cell doesn't have it, then it doesn't want it. So if this A red blood cell doesn't have any Bs on it, it doesn't want Bs, so it's going to build an army against Bs. Antibodies are found in the plasma, and they're there to essentially attack any kind of B blood that might come into contact. So if you're a person with A-type blood and the doctor accidentally gives you B blood, this anti-B antibody is going to attack that B blood. So this whole thing is in one person's blood. The red blood cell with the antigens on the red blood cell, and then the antibodies in the plasma. B-type blood has B antigens, and because it's B, it doesn't like A, so it's going to make an anti-A antibody. AB blood has A and B antigens, so it likes both of them. If it likes both of them, is it going to make any army against A or B? No. So, no antibody. People with AB blood do not make antibodies. Then you have type O blood. Type O blood has no antigens on it, and therefore it doesn't have A, it doesn't have B, it doesn't want A, it doesn't want B, so it's going to make an army against A and B. So although O doesn't have any antigens, it makes both antibodies. So here's the type of question I could ask. Could someone with A blood donate to someone with A B blood? Now, I got to give you a little side fact before you can answer this question. When you donate blood, you only donate the red blood cells. They take all of the antibodies out of it. You're not donating the plasma when you're doing a red blood cell donation. So if you're donating A blood, you're just donating the A blood. You're not donating these B antibodies with it. So now again, with that being said, if you're A-type blood, can you donate to someone with AB blood? The answer is yes, you can. AB blood has A and it has B, so it's fine accepting someone who's also an A. Now let's turn the tables. Can someone who has AB blood donate to someone who has A blood? The answer is no. Why? Well, AB blood has A antigens and B antigens. You can only donate what's familiar to this person. And this person only has A antigens. This person only has A, they only want A. So if you donate the B, it's going to be an issue. So again, when you're donating the blood, you're only donating the red blood cell. The person receiving the blood has the red blood cells, but it also has the plasma. So if you're donating AB blood to a person who has A blood, what is found in the person with A blood's plasma? Let's look here. A blood. What's in their plasma? An anti-B antibody. Anti-B antibody, anti means against, is going to fight against B blood. So when you donate AB to this guy, the anti-B antibody is going to attack that B antigen. So if you notice, the antigen and antibody are the same colors. Anti-B antibody attacks B antigen if it sees it. Anti-A antibody attacks A antigen if it sees it. This just gives your body a way to protect yourself against blood types that don't belong to you. There will be a worksheet that you will do on this. I will post it and talk about it in an email that I'm going to send you guys, but be sure that you're okay with blood typing, and if you are not, make sure to set up a Zoom meeting with me. So the functions of the heart are not very various, but there's some pretty important ones that I do want to point out. Number one is to generate blood pressure. The harder the heart pumps, the stronger the pressure of the blood is going to be. It routes the blood both to the systemic and pulmonary circulations. It ensures that blood constantly flows in one direction, from artery to capillary to vein, and then back around. You will never have blood flowing in two directions within one blood vessel. And the last one is to regulate the blood supply. It's able to auto-regulate to control and set heart rate as well as blood pressure dependent on the metabolic needs of your body. So in terms of the structure of the heart is made up of three layers: the epicardium, which is the outermost layer, the myocardium, which is the thick muscular layer of cardiac muscle, and the endocardium, which is the inner lining of the chambers. Where we're going to focus is the myocardium, the layer of cardiac muscle that actually contracts to have a muscle contract, have the blood pump out of the ventricles and out of the outgoing blood vessels. So again, this is now the second time I'm showing you the blood flow through the heart. I've also given you a schematic. Make sure you know this pathway, or else you're going to struggle with the electrical system of the actual heart. Now, this is where we start with the electrical conduction system of the heart. Everything in yellow is part of that conduction system. We start at the upper right region at the SA node. The SA node conducts electricity. The electricity shoots down the right atrium, across the top of the atria to the left atrium, and on its way down, it's going to then encounter the AV node. The AV node then sends the electrical circuit down the AV bundle, which is right here. The AV bundle branches off into the left and right bundle branches until you reach the apex of the heart, which is the bottom tip. From here, the bundle branches move up the myocardia of the ventricles, and they are called Purkinje fibers. This is the pathway of electrical conduction through the heart. Make sure you know this pathway. So by understanding this pathway, you'll be able to understand the contraction cycle of the heart. So first, the atria will contract down, and then that voltage will shoot down the inner ventricular septum and back up, causing the ventricles to contract up, pushing blood up and out of the aorta and the pulmonary artery. So let's talk a little bit about electricity. Before I talk about this, let's remind ourselves of the terms depolarization, which is an increase in voltage, repolarization, which means coming back down to our resting membrane potential, and hyperpolarization, which means going more negative than our resting membrane potential. So the conduction of electricity through the heart, we call it action potentials. Your conduction system creates action potentials, or voltage surges, that are going to travel from the atria down and up the ventricles. It is caused by a rapid depolarization and then a rapid repolarization. Your heart must depolarize, then repolarize. Depolarize, repolarize. Basically, it means contract, relax. Contract, relax. Now, we'll talk about voltage-gated channels as well. And voltage-gated channels have a huge role in this conduction system, and that'll be more in the next PowerPoint that we're going to do, called cardiac physiology. Let's start by talking about the SA node, the first place where we actually see generation of action potentials. The SA node and the AV node are specialized regions of the heart, and they're specialized because they're made up of a specialized cell called a pacemaker cell. Pacemaker cells are different than regular cardiac muscle cells. And one of the facts that I want you to know about them is that pacemaker cells have an abnormally high resting membrane potential. Whereas the resting membrane potential for other cells in your body is around -70, pacemaker cells have a resting membrane potential at around -50. So they're a little bit higher than usual. This illustration shows it at around -60. So the higher you are in your resting membrane potential, the closer you're going to be to what's called a threshold. The threshold is the minimum voltage you have to slowly reach before shooting off an electrical surge. So these SA and AV node regions are made up of pacemaker cells, which have a higher than normal resting membrane potential, which means they're closer to the threshold and will more easily shoot off a voltage. This is actually very good because you definitely don't want to make it difficult for your heart to reach threshold, shoot the voltage to actually make your heart beat. You want to make it as easy for your heart as possible to do each beat. Why? Because does your heart ever take a break? Nope, not until you die. So here are the steps of how pacemaker cells work. There are 3 steps I want you to remember. The first step is called the slow depolarization. You're slowly moving up in voltage until you reach the threshold. Once you reach the threshold, you shoot up in the rapid depolarization phase. And then that's where your muscle contraction happens. You've got to recharge the heart muscle, so you relax and go through the repolarization phase until you go back down to your resting membrane potential. This is what happens in pacemaker cells. We are going to look more into pacemaker cells. Before we do that, let's cover a few more terms. The term refractory period refers to the amount of time that's required for rest between each depolarization. You need to give your heart some time to rest before the next contraction happens. So here at the bottom, you see the stimuli. Let's say we're going to stimulate the heart muscle to do a contraction. So you provide a stimulus. It does the slow depolarization, reaches the rapid depolarization, and comes and relaxes back down. Now, you can give it a second stimulus and hope that it does another action potential, but notice that it doesn't. Why? Because we're in the blue region here. This is called the absolute refractory period. This is the resting period after a contraction where you absolutely cannot have any other new depolarizations or contractions. Even if you gave it a stronger stimulus, as you can see here, it still doesn't allow it to do a second contraction. So when can we do our next contraction? Well, you got 2 options. If you're wanting to do it quickly, rapidly, you can do it pretty soon after during this orange period here. This is called the relative refractory period. During this period, you can have a second contraction. However, you do have to provide a pretty strong stimulus, and the actual strength of that contraction is not going to be very high. However, if you do want a nice strong contraction, you should probably wait until after the relative refractory period, where you can provide a stimulus, generating a nice strong contraction that was the same strength as your initial contraction. So again, differentiating between absolute and relative refractory periods. During the absolute, you absolutely cannot have another contraction, no matter how strong of a stimulus you give. During the relative refractory period, you'll be able to actually provide a strong stimulus. However, the strength of the depolarization is not going to be as strong. This could result in a very weak heartbeat, causing low blood pressure. This is an issue that can happen in people with some conduction disorders of the cardiovascular system. So this next portion is pretty important, and I'd like you guys all to know how to read an electrocardiogram. And these guys show you the electrical conduction of the heart, which means it shows you voltage changes. As you can see from the y-axis, it's measured in millivolts, and on the x-axis, it's measured in seconds. So we have the P wave, the QRS complex, and the T wave. So an ECG will measure action potentials, voltages moving down the heart, voltages moving up the heart. Anytime you see an upward curve, that means the direction of the voltage is moving from the atria down towards the ventricles. So a P wave and a T wave, this is going to be in the direction moving down towards the apex of the heart. This Q, the little S here, those will indicate movement upwards, and then the R wave is the big movement downwards. And really what this QRX complex shows, and rather than taking it piece by piece, take it as one whole complex, is the summation of the voltages shooting down and up the ventricles. Because the ventricular contractions are the strongest ones, you can bet that they're going to be the largest in their voltage change, hence the largest wave here. So the pattern is going to be the P wave first. And the P wave represents atrial depolarization. So that means the atria shooting the voltage from the SA node down the AV node, hence the upward curve. Now, do you need a lot of voltage to go from the top to the bottom of the atria? Probably not. It's not a very large compartment, nor do you need a very strong voltage there, because you're not contracting very hard in the atria. The atria contract to pump the blood where? Well, right down to the ventricles. It's like maybe an inch or two away. Really close. So once the blood goes from the atria to the ventricles, then you have the QRS complex. This is when the voltage shoots down the bundle branches and back up the edges of the myocardium surrounding the ventricle. And that's going to be a curve that goes down, up, and down. Again, it's the net voltage that you have when the ventricles are contracting. So first, the voltage shoots down the interventricular septum, then up the ventricles to cause that ventricle to contract, pumping the blood up and out of the pulmonary artery and the aorta. The last piece of this is going to be the atrial repolarization that takes place here as well. So not only are the ventricles contracting during the QRS complex, but the atria are recharging. And then the last wave here is a T wave, and it goes upwards, which means it's a downward moving voltage. And the only thing that's happening in the T wave is ventricular repolarization. You repolarize by bringing those ventricles from a contracted mode down back to a relaxed mode. And because the ventricles are recharging in the downwards direction, it's going to be an upwards curve. So again, atrial depolarization, ventricle depolarization, and atrial repolarization, and then ventricular repolarization. Now, some things that can go wrong with the conduction systems is going to be misfiring of those nodes, like the SA node or the AV node, or multiple nodes firing at the same time, and causing the heart rate to either beat too fast, which is tachycardia, beat too slow, which is bradycardia, or you can just have irregularities, which we call sinus arrhythmia. This usually happens during your respiratory cycle or during deep respiration. You have premature atrial contractions, and just like the name states, this is when the atria contracts before the entire conduction cycle has completed one full electrical circuit. And this can happen in healthy people. So if sometimes you feel like your heart might be doing a weird bubbling beat, or it feels like it skipped a beat, oftentimes it's a premature atrial contraction. This can happen for three big reasons: lack of sleep, high stress, or high caffeine. All of those can cause premature atrial contractions. Now, this is probably one of my favorite slides only because it shows you the ECG along with what it correlates with in the heart, and it has little arrows in it to show you the directionality. So the P wave, again, upward curve because it's a downward motion of voltage. So the atria are contracting here and depolarizing, so downward movement of voltage. The QRS complex is going to be a compilation of that voltage shooting down as well as up. So that's going to be your QRS complex. And then the T wave, again, is an upward wave for the downward repolarization. So pretend that this ventricle is contracted, and let's kind of draw what it would look like when it's contracted. So it's all contracted up here and it's squeezed up. It needs to repolarize back in the downward motion, hence an upward curve. Now, this is the ECG of a normal heart rhythm. You have your P wave here, you have your QRS here, and the T wave here. A fast heart rhythm, what do you see as the biggest differences between normal heartbeat and the fast heartbeat? QRS looks pretty similar, but what I'm seeing is that the spacing between the P wave and the T wave in between rhythms has dramatically shortened. And same with the slow heartbeat, the distance between the T wave and the P wave has dramatically increased. And then this, as you can see, you've got some sort of irregularity, which we call arrhythmia. And we've got a fast heart rhythm here, we've got some delays here, and then it goes to normal here. So understanding ECGs in terms of each of their respective components will help you kind of understand what's actually happening in the heart when you do have to read an irregular ECG. Now the cardiac cycle, because it has atria and ventricles, we consider it a two-pump cycle. And we have the right side atria ventricle and the left side atria ventricle. The right atrial ventricle is one pump, pumping blood towards the lungs. The left side is the part of the heart pumping blood towards the systemic circuit. Now, we have repetitive contractions, and every time the ventricle contracts, that high voltage, high pressure contraction is called systole, and then the relaxation of the ventricle is called diastole. That blood will eventually move out of the aorta all the way towards the rest of the system, slowly moving down its pressure gradient. Now, go ahead and star this slide because this really does show you what's happening at each phase of contraction. I'm going to go through this really slow, and you can watch this as many times as you need to remember all these terms. So here is your heart. Remember, you have AV nodes and you have SA nodes. So we're going to start at a point of systole and contraction. That'll be our step one. So you see the ventricles are contracting, and they're starting their movement inward. So the ventricle muscle is beginning to contract, pushing the blood towards the semilunar valve here and the semilunar valve here. This is called systole. This initial phase of systole is the isovolumetric contraction phase, where the volume of blood in the ventricles doesn't change, hence isovolumetric. However, the muscles here and here are contracting. Now, once these muscles contract with a strong enough force, then we'll go into what we call the period of ejection. This is when you've pushed up hard enough to be able to open up the semilunar valves and push that blood out of the ventricles and into the blood vessels. So both of these were systole, the start of systole and the end of systole. Now at this point, the heart needs to rest. The resting phase is called diastole. This is called isovolumetric relaxation. Isovolumetric because we're keeping the volume consistent in the heart, which means we're not filling it with anything, we're not letting anything out of it, but we are allowing the muscles to go back into relaxation phase. I want you to notice that all 4 of the valves are shut, so there's no movement of any of the blood in or out of the compartments. Once the muscles have relaxed, meaning Once we're out of the absolute refractory period, and in a normal person out of the relative refractory period, we are going to begin the diastolic passive filling phase. And it's passive ventricular filling. Why passive? Well, because you notice the atria are not contracting yet, but they are filling with blood, and some of that blood generates enough pressure to already make its way down into the ventricles. Now, not a lot of blood is going to be getting into the ventricles at this point yet, just a little bit. Hence, we call it passive ventricular filling, and it's termed diastole, again, because the ventricles are in its relaxation state. The last step of diastole is going to be the active filling. So we are going from passive filling to active filling. What is the biggest difference you see from passive filling to active filling? Well, active filling, you see these lines here? That means the muscles in the atria are contracting, forcing that blood down the ventricles. So this filling phase is going to be where the bulk of the blood goes from atria down into ventricles. And again, it's because the atria are finally contracting. And then we move back up to step 1, where we now begin the ventricular contraction. So 2 steps of diastole, 2 steps of systole, and 3 steps of diastole. Now, when a doctor uses a stethoscope to listen to your heart rhythms, what exactly are they listening for? Well, they're not listening for the beat of the heart. What they're listening for is for the lub-dub of the heart. These guys are the sounds made by the valves. So the AV valves versus the semilunar valves. Every time AV valves shut, they should be shutting with a very hard slap. That is the initial sound. They call it the lub sound. The second heart sound comes from the semilunar valves slapping shut, the dub sound. So lub-dub, lub-dub, lub-dub. That lub-dub sound indicates whether or not your valves are closing hard enough, if there's backflow, if there's a flutter. These guys can be detected when using the stethoscope. Of course, they also use stethoscopes for listening to breathing sounds, but right now we're talking about the heart, so we'll stick with just cardiovascular. Now, this one is a big star. Let's big star this guy. This is the equation you have to memorize, and this is the equation for mean arterial pressure. And you might remember now that I already gave you an equation for mean arterial pressure in the last presentation. You can use both to solve for the map. Depends on what variables I give you. In the last equation, if I give you systolic and diastolic blood pressures, you're going to use that equation. In this one, if I give you cardiac output and peripheral resistance, this is the one that measures mean arterial pressure. So mean arterial pressure is the average blood pressure that comes out of the aorta. It is dependent on the cardiac output and the peripheral resistance. Cardiac output is the amount of blood pumped by the heart every minute. So if you collected the entire volume of blood that your heart pumped out in 60 seconds, that would be this volume. But we have a mini baby equation to solve that. Cardiac output is equal to the stroke volume times the heart rate. Heart rate, of course, is beats per minute. Stroke volume, like the name states, is the volume of blood per stroke, aka beat of the heart. So, how much blood does your heart pump out in one beat? And then how many beats does it do in 1 minute? So if you put all this together, you essentially have mean arterial pressure equals stroke volume times heart rate times peripheral resistance. And that peripheral resistance value is going to be the resistance by which the blood has to move through the blood vessels with. I will give you the numbers for stroke volume, heart rate, and peripheral resistance. You will just need to remember this equation and multiply them all together to give me mean arterial pressure. Now, the next 2 slides, this is something that I am going to cover over Zoom because this is something that we have to, I think, do together. It's going to be most effective to do together. But if I can just introduce this to you, this is going to be the factors affecting mean arterial pressure. If you go back, again, the factors are stroke volume, heart rate, and peripheral resistance. You'll notice that I've given you some scenarios. And what I need you to do is just cross out this box. I don't need you to see chapter 21. So here are some factors. A decrease in blood pressure, decrease in blood pH, so on and so forth, will cause this to happen. Increased sympathetic stimulation. If this happens, that'll cause these two to happen, and you can just follow the arrows and follow the pathway, ultimately increasing mean arterial pressure. Follow these pathways, and these are something that I'm, again, going to cover in our next Zoom meeting on Tuesday. And this kind of gives you a step-by-step for what occurs. This is like the big review slide of what we went over in this PowerPoint. This one is one I'm going to go over with you now. How to regulate the heart. The heart is regulated intrinsically, that means on its own, or extrinsically, that means through external forces. Intrinsically, the heart has autoregulation. Remember the Frank Starling law of the heart? The more the heart stretches, the stronger it's going to contract. This is intrinsic regulation, the heart controlling its own contraction cycle. Extrinsic regulation is going to be externally controlling the heart, and two ways to do that is with neural and hormonal control. The neural control is going to be this part, the parasympathetic and sympathetic response. Parasympathetic innervation is done through what's called the vagus nerve, and this helps to decrease your heart rate and relax you. The sympathetic stimulation is done by cardiac nerves. This is all about panicking and the fight or flight response. So we're going to increase the heart rate, we're going to increase contractility, and we're going to release the hormones epinephrine and norepinephrine. And then, of course, we have other external factors that can affect the entire cardiovascular system. And we're going to look at these four now. These are actually pretty interesting. The effect of blood pressure. Inside your heart, as well as inside your arteries, you have baroreceptors. And baroreceptors are receptors that monitor your blood pressure. If the blood pressure rises in the heart rate will slow down to make up for it. Your goal as a homeostatic individual in a normal day-to-day function is to make sure the cardiac output remains consistent. So if your blood pressure goes up, you want your heart rate to come down a little bit. The next one is the effect of pH. Remember, if carbon dioxide goes up, that usually means oxygen has gone down, and that will also cause the pH to also go down, which means you become more acidic. When you have a low pH and you're acidic, what does that mean you have a high concentration of? If you're very acidic, what do you have a high concentration of in your blood? H plus ions. Ultimately, this is a chemical, right? So when you have a lot of hydrogen ions, they bind to chemoreceptors. Just like how there's baroreceptors all over your body, there are chemoreceptors as well. These guys are usually localized to the arteries directly leaving the aorta, as well as in the brain. When your brain measures the concentration of protons, it could say, hey, listen, there's a lot of protons in the blood. That means we're pretty acidic, which probably means we have a lot of carbon dioxide. Let's go ahead and increase the respiratory rate. Or let's go ahead and increase the heart rate to get rid of some of this carbon dioxide. Third one is the effect of extracellular ion concentrations, like potassium. When the potassium levels outside of the heart increase, it lowers your heart rate. This is why they say when you're anxious, what fruit should you eat? You should eat a banana. High in potassium, it actually decreases your heart rate. And the last one is body temperature. Body temperature is correlated to heart rate with a direct correlation. As temperature goes up, the heart rate also goes up. As temperature goes down, your heart rate also goes down. So if you could just go through and remember these correlations, that would be wonderful. So this is the illustration that goes along with it. The green ones are the ones that are the incoming signals. Remember, they are afferent sensory signals. They come from baroreceptors or chemoreceptors, and they send signals to your brain, specifically the brainstem. The brainstem integrates it and sends output signals. So if it has to lower your heart rate, it sends it out through the vagus nerve to the SA node to say, hey, SA node, slow down. But if it has to increase the heart rate, it goes ahead and sends a signal out of the sympathetic nervous fiber, again to the SA node to say, hey, speed up, but also to the muscles of the heart to tell them to contract harder. This last one is the endocrine innervation, where if you need your heart to speed up, you're going to innervate the adrenal gland. That makes epinephrine and norepinephrine, which are basically adrenaline. They go into the blood, and that blood goes to the heart, and when epinephrine and norepinephrine bind to the heart, it causes the heart to speed up and beat harder. So these two diagrams that we have, so this one and the next one, they are the same format. I will let you know, it seems like a lot of information, but it's just really wordy, and I couldn't take out any of these words. This illustration was not editable from the publisher, so I will let you know that it's very wordy. You can really seriously put like one bullet point in each of these and it would be as effective. So I'll go through one of the sides and then you can go through the other on your own. So let's say there's a sudden drop in your blood pressure for whatever reason. What kind of receptor senses that? So if you have a decrease in blood pressure, the baroreceptor senses that. The baroreceptor will send a signal to your brain, and because blood pressure dropped, your brain says, hey, that's not good. If blood pressure dropped, we might not be getting enough blood to the rest of the body. So what nervous system response can I then start to get more blood pumping faster to the rest of the body? Well, I can increase my sympathetic nervous response. I can also stimulate the adrenal gland to make epinephrine and norepinephrine. When you increase the sympathetic response and you make those stress hormones, it's going to ultimately cause the heart rate and stroke volume to increase. When heart rate and stroke volume increase, that causes your blood pressure to also increase. The next one is about chemoreceptors. Let's say there's a drop in your blood pressure. There's a drop in your blood pH. If blood pH goes down, so you have a lower pH, does that mean you're acidic or is it basic? Well, lower pH indicates that you're acidic. If your blood pH drops, it's usually because you have too much CO2 in your system. So chemoreceptors will sense this increased acidity in your blood. And they'll say, hey, there's a lot of acid in the blood. This must mean there's a lot of carbon dioxide in the blood. And if you have a lot of CO2 in your blood, what gas do you not have in your blood? Probably don't have that much oxygen. So you send that signal to the brain, and because the goal is to get more oxygen in, you're going to, again, increase the sympathetic response to breathe faster, get more oxygen in, get your heart rate up to get that carbon dioxide back out to the lungs to breathe out. And because you're going to increase the sympathetic stimulation as well as the adrenal medulla again, you're going to increase the heart rate and the stroke volume, ultimately being able to breathe in more oxygen, pumping out more carbon dioxide, and bringing that blood pH back up to normal values. So be sure you're going through these two slides, and I'll tell you something. If you know one side of it, you also know the other side of it. Why is that? Well, it's just the opposite. So if this is a decrease in blood pH, this one's going to be an increase in blood pH. If this is increased sympathetic response, this is going to be increased parasympathetic response. Increase heart rate, decrease heart rate. Increase blood pH, decrease blood pH. So if you learn one side of it, you basically already know the other side of it. Effects of aging on the heart. You guys can go ahead and read through this yourself. This slide is actually very interesting. So be sure that you read this on your own. Other than that, these were your two introductory PowerPoints on the cardiovascular system. If you can finish these and move on to cardiovascular physiology, that would be wonderful. Again, I will be giving some of this content in our next Zoom meeting to prepare everybody to begin that cardiovascular physiology lecture. But again, that cardiovascular physio lecture is a tough one. You're going to want to get a head start on it. And then we will talk about it at our next meeting. And I will kind of give you guys a little bit more guidance on how to navigate cardiovascular physiology, especially because I'm going to be actually covering some of it during our Zoom meeting. Hope you all have a great weekend, and I will see you guys next week. Bye.